Our next lesson in the reaction and stoichiometry unit is on reaction types. Here are the two learning targets we have for this video. The first of which we want to be able to classify basic chemical reactions. We have 5 different classifications for reactions that we will use. The first is synthesis, the next is decomposition, followed by single displacement, or sometimes referred to as single replacement. They are one and the same. We have double displacement, or again double replacement, and then the fifth is combustion. One note that should be mentioned at this point: this is simply one method for classifying reactions. There are certainly other classification categories or other classification systems that can be used. This is the most basic and the one that will be best used by us in class, so that's why we stick with this one. So what we'll do now is we'll look at each of those reaction types, and we'll look at what some basic reactions would be that would fit into those categories, so you get a sense of how to classify each of these reaction types. So we'll start with synthesis. In a synthesis reaction, 2 or more reactants are going to form one product. So there's your key there. If you just have one product, that tells you it is a synthesis reaction almost always. So the general form, just using some generic symbols here, would be A plus B, where A and B could be elements or compounds. A lot of times they are elements, and then they combine to form a compound of A, B put together. So some examples of this would be the formation of water from hydrogen gas and oxygen gas. I'm not showing the physical states here, but notice the key here is we just have one product. The fact that we need 2 molecules of water to balance the equation has no impact on what reaction type this is. So we could just as easily leave out the coefficients here, have an unbalanced equation, and it would still make it synthesis, or if by balancing it, it doesn't make it not synthesis, the fact that there are two molecules of the water here. That's still just one product. We just happen to get 2 molecules of that same product. Here would be another example, the formation of sodium chloride. Again, notice we have 2 elements here, in this case sodium and chlorine, and they are combining to give us a compound, sodium chloride. Decomposition. Decomposition is when we have one reactant that is going to break down into 2 or more products. So this is just the opposite of synthesis. So in a decomposition reaction, we have some compound, and there's only one reactant. That's the key there. If you identify one reactant, that tells you it's going to be decomposition. And then it's going to break down into at least 2, if not more, products. So here are some examples. The first example is just the reverse of the first example that I showed you on synthesis. Here we have a molecule of water, actually 2 molecules of water, but notice it's just one reactant, and then that breaks down into the components hydrogen and oxygen. Here is a slightly more complex example where we have a compound. This would be ammonium carbonate, and that's breaking down into 3 products. And one thing to notice here is the products don't necessarily have to be lone elements like we see up here in the water example. Notice on this example we have ammonia, carbon dioxide, and water as products, so it doesn't have to be an element as a product there. Let's take a look at single displacement. In a single displacement reaction, a free element replaces a like charged element in a compound. And here's what we mean by that. 2 different examples here for the general equation, or the general form. A, in this example, is a free element. Okay, so it's an element that's not in a compound with anything else. It's going to react with a compound. Oftentimes it will be a binary compound, meaning a compound made of just 2 elements. And then A will replace or displace the element that's in this compound that has a like charge. So for example, if A is a metal, meaning it would form a cation, a positively charged ion, it will take the place of the cation in the compound, and then that ion, that cation, would get kicked out or displaced as the lone or free element. So notice here our products are AC, where A has displaced B to take its place, and then B is now kicked out by itself. Or we could have this situation over here on the right. If A is a nonmetal, meaning it will form an anion, it will take the place of the anion in the compound, and then that anion would get kicked out as the free element. So in this case, we get Ba as a product, and then we get C as the free element. So let's look at some examples here. So in this first one, we have barium reacting with sodium oxide. Barium is a metal. It will form a cation, so it will take the place of the metal or the cation in the compound. So notice the barium takes the place of the sodium, so we now have barium oxide instead of sodium oxide, and the sodium gets kicked out as the free element. In this next example, our free element here is chlorine. Okay, chlorine is not in a compound with anything else, so it will take the place of the like-charged ion, in this case an anion, the nonmetal in the compound, so it will take the place of bromine. So instead of having potassium bromide, we now have potassium chloride, and then bromine gets kicked out as a free element. One note about these products here. Take a notice that when we write the formulas of these products, these subscripts are very likely to change from what they were on the reactant side. We could have said the same thing before about the synthesis and the decomposition reactions as well. So notice, just because I have two sodium atoms or two sodium ions on the reactant side, on the product side I might not have two of them. Now, if I want a balanced equation, I would then need to go in and add coefficients, as we know how to do. But you just have to write the formulas so that the compound formula is correct. The formula for sodium oxide is Na2O, because sodium is 1 plus, oxide is 2 minus, so we need two sodiums. Whereas barium oxide is just BaO, because barium's 2 plus, oxide's 2 minus, so the ion charge will cancel. Likewise, same thing here. Just because I have Cl2 here, chlorine's diatomic, does not mean my formula for the product will be KCl2. You just have to write the formula as you know how to do, and then if you need a balanced equation, you can go in and balance it from there. Alright, the other displacement reaction is a double displacement reaction. In a double displacement reaction, what happens is ions simply exchange between two ionic compounds, and this often occurs in solution. Actually, in the next video, it's kind of a second part to this video here, I'll give you more explanation for that. But for now, let's just take a look at the general idea of what this is. So in a double displacement reaction, we always have two compounds. In this case, I'm showing AB reacting with CD. So what happens is we can think of either the anions or the cations, either one, switching places. The thinking works the same either way. So in this example here, the arrows I'm showing the anions switching partners. So B takes the place of D, D takes the place of B. So we started with AB plus CD. Our products are AD. Notice I still have cation, anion listed in the formula. I can't match up two cations and I can't match up two anions. And then I have CB as my other product, where those two anions have simply switched places. So let's look at some examples here. For these double displacement reactions, we'll see three basic ideas that can occur as far as different types of double displacement reactions. And again, in the next video, you'll get some more details on this. So in this first example, we have a precipitation reaction. And what that means, recall we've talked about this before, is that we have a solid that forms from solution. So I'm mixing two solutions together, in this case copper 2 chloride and sodium phosphate, and then one of my products is insoluble in water, meaning it will not dissolve. That happens to be the copper 2 phosphate. Now how do we get that? Well, all that happened is the copper ion, the cation from one compound, and sodium, the cation from the other, switch places. So the copper is now in a compound with the phosphate ion. We can see that here. And then the sodium is now in a compound with the chloride ion. We can see that here. And sodium chloride is soluble in water, meaning it will be aqueous. Again, notice what I mentioned on the last slide. When you write the formulas for these, you just have to write the formulas so that the charges cancel. Notice, just because I have one phosphate ion here on the left side does not mean there will be one phosphate ion on the right side in the formula. If I wanted a balanced equation, I would need to go in and balance it from here. Another type of double displacement reaction that can occur is called an acid-base reaction, or often referred to as water-forming reaction. Here we have sulfuric acid, H2SO4, reacting with potassium hydroxide. All hydroxide compounds are bases. So I have an acid reacting with a base. If I think about the double displacement, what occurs here, again, I can just think about the cation switching places. The hydrogen ion from the sulfuric acid will combine with the hydroxide ion in the potassium hydroxide. So that would give us HOH. Well, that's H2O. That's water. That's what we see here. And then my other product would be the potassium ion combining with the sulfate ion. That's where we get the potassium sulfate. So anytime we have an acid-base reaction or an acid reacting with a hydroxide, we'll always get water as a product because the hydrogen from the acid will always combine with the hydroxide from the base, and that will give us water. And then we'll get some other salt. That would actually be the cation from the hydroxide combining with the anion from the acid. That would always be the case in those types of reactions. Alright, the other type of double displacement reaction we'll see is often referred to as a gas-forming reaction, and this always occurs whenever we have an acid reacting with a carbonate, or it could be a bicarbonate compound, and that's the example we have here. This example, we have acetic acid, we have HCH3COO, that's acetic acid, reacting with sodium bicarbonate, and that gives you sodium carbonate, and notice that's the cation with the anion from the other one. Excuse me, not sodium carbonate, sodium acetate is what we get here. That's the sodium ion combining with the acetate ion from the opposite compound. And then we actually get two more products. You might be wondering where these come from. Well, what this is the hydrogen ion from the acid combining with the bicarbonate ion. And notice if I write that, if I just add the hydrogen to the bicarbonate ion, that would give us H2CO3. Well, what actually happens when H2CO3 is formed, that's called carbonic acid, it immediately breaks down into water and carbon dioxide. So notice what we have here. If I would combine these two formulas here, the water and the carbon dioxide, there's two hydrogens, there's a carbon, and there are three oxygens between those two compounds. That would be your H2CO3. Now the reason we call this a gas-forming reaction is we get this carbon dioxide gas formed. You're going to see bubbles when this happens. This reaction here, this equation, is your classic baking soda and vinegar. The acid that's in vinegar is acetic acid. The baking soda, that's sodium bicarbonate. And the reason you get bubbles, the reason why it fizzes up, is you get carbon dioxide gas formed as we see here. As I've been mentioning, the next video will clarify some of this. This is just a quick rundown of these reaction types. The next video will focus on the displacement reactions and some more details. So if you're a little confused by some of this at this point, that's really not a big deal. Alright, the last reaction type we want to be familiar with is known as a combustion reaction. In a combustion reaction, that means we have a compound or an element that's burning in air. Well, ask yourself, what does it mean if something's burning in air? What is it reacting with? Well, the answer to that is oxygen. So the general form here, we have AB, where AB would be a compound. It could also just be an individual element. So I could just write this as A plus O2. And O2 will always be a reactant in a combustion reaction because we're always burning it in air, meaning oxygen's always there. If you don't see O2 as a reactant, then it is not combustion. And then in this general equation here, our products would be AO, where AO would be some oxide of the compound A, or of the element A, so A will combine with oxygen, and then B will also combine with oxygen to give us BO, where again, that would be some oxide containing the element B. So let's look at some examples here. The first one, we have sodium reacting with oxygen. And in this case, this is the example where we have an element burning in air. We actually only get one product. We just get the sodium oxide. So just imagine our general equation here. If the B was not present, then we would not have a second product here of B combining with O. Now you might also notice that this is the exact same form as a synthesis reaction. So we would actually categorize this particular reaction here, this sodium reacting with oxygen, we would categorize it as both a synthesis reaction, because we're forming one product from more than one reactant. We would also classify this as a combustion reaction because we are burning it in air. Here's another example. We have methane, that's CH4, reacting with oxygen, as is the case with all combustion reactions. Notice the products here. We get carbon dioxide, so there is the oxide that contains carbon, and then we get water. That is the oxide that contains hydrogen. So notice if we look at our general form, it's not necessarily just, in this case, CO and HO. These products, as far as how many atoms, will vary based on what the elements are that are present. However, a good piece of news here for you. If our reactant with oxygen is a hydrocarbon, notice here we have a hydrocarbon, meaning it's based on carbon and hydrogen. You will always get these as your products, carbon dioxide and water. So whether this is CH4, being methane, or whether it's octane, which would be C8H18, or propane, which would be C3H8, it makes no difference. These will always be your products, the carbon dioxide and the water. So you might want to jot that down on your sheet there if you have if you're taking notes along with the lesson here. Makes it easy to remember the products for these reactions. All right, here's a practice problem. I've just given you several equations here. I want you to go through and I want you to classify each reaction. So pause the video, classify each one, and then see how you did. Alright, I suppose you've had a go of classifying these. Here are the answers. The first one is a single displacement reaction. I know this because I have a free element replacing an element in a compound. The copper replaces the silver, so that is single displacement. B is double displacement. I know that because I have ion switching partners. The silver takes the place of the sodium takes the place of the silver, so that makes it double displacement. C is combustion and also synthesis. It's combustion because O2 is a reactant. The copper is burning in oxygen. And it's also synthesis because I'm taking more than one reactant and forming one product. So that would be a synthesis reaction. D is single displacement. I have a free element, in this case fluorine, taking the place of bromine, and then the bromine gets kicked out by itself, so that is single displacement. E is decomposition. I have one reactant that is breaking down into more than one product, so that's decomposition. F is combustion, and only combustion. I have O2 as a reactant, so that tells me it's combustion. I'm burning ammonia in this case, and that gives us our oxides here. This would be nitrogen monoxide, and obviously H2O is water. And then finally, G would be decomposition. I have one reactant, and then it is forming more than one product, so that makes it decomposition. Alright, so we should be able to classify basic chemical reactions from what we've seen there. What we should also be able to do is to predict products of some simple chemical reactions. So let's just take a look at what that means. Based on what we've learned with these reaction types, if we understand the patterns of each of those types, what that allows us to do is to predict fairly accurately what we'll get for a product or products of reactions. So let's take a look at an example. Let's say I ask you to predict the product of the following reaction. We're reacting rubidium with magnesium oxide. If you take a look at the identity of the reactant, or in this case reactants, that will tell you what type of reaction to predict. In this case, a single displacement reaction is by far the most likely, and the reason I know that is I have a free element, in this case rubidium, reacting with a compound, in this case magnesium oxide. So based on the patterns of the reaction types, the rubidium will replace the like charged element in the compound. In this case, that would be magnesium. Because the rubidium will form a cation, it will replace the cation in the compound. So that's what we're showing here with the arrows. The rubidium will take the place of the magnesium. The magnesium will get kicked out as a free element. And now we just need to write the formulas of the products. So in this case, that would be rubidium oxide, which would be Rb2O, and we'd also get magnesium. Here's another example. Let's say I ask you to predict the product of this reaction. Notice in this case, sodium chloride is the only reactant. Well, based on the reaction types that we know, there's only one possibility for what reaction type can occur, and that is decomposition, because there's only one reactant there. So what's going to happen is the sodium chloride will break down into its component elements. So we just need to write the formulas of those elements. In this case, that would give us sodium, and it would give us chlorine. Notice chlorine is Cl2 because it is diatomic. Now here are some more examples. Let's say I ask you to predict the product of this reaction, aluminum plus oxygen. This will be synthesis. It would also be combustion. Probably easier to think of this as synthesis. I have two elements reacting. There's only one possibility. I can't replace anything because there's not a compound to replace an element in. So we'll have synthesis. So my product is just going to be a compound of those elements combining together, and that would be aluminum oxide, which has the formula Al2O3. Again, a point in writing these product formulas, I mentioned this earlier, we cannot just look at the reactants and use the same subscripts. So I cannot look here and say, well, this should be AlO2 because those are the subscripts over here. You just have to write the formula correctly. Aluminum is 3 plus, oxide's 2 minus, so that's why we have this formula. You can then go in and balance the equation if that is necessary. Alright, here we have Na3PO4 plus CuCl2. In this case, we would predict a double displacement reaction because we have two compounds. And so in this case, the cations or the anions, either one, you can think of it either way, will simply switch places. Okay, so we'll switch the ion partners. So that means the sodium will go in place of the copper, so that would give us sodium chloride, and the copper will take the place of the sodium to give us copper phosphate. Okay. One note about the product here, with double displacement reactions, whatever charge the ions have on the reactant side, they will maintain the same charge on the product side. So what I mean by that is this. Here on the reactant side, this copper is a copper 2 ion. I know that because it's CuCl2, the chloride's 1 minus, so the copper has to be 2 plus. So the copper will still be 2 plus over here. So this is copper 2 phosphate. This is an important point whenever we're dealing with metals that form multiple charges on their cations, as we know can happen quite often. So if it's 2 plus on the left side, it will continue to be 2 plus on the right side. Alright, here we have lithium bromide reacting with fluorine. Here we would predict a single displacement reaction because I have a compound reacting with a free element. The free element, in this case fluorine, will displace or replace the like charged element in the compound, which would be the bromine. So that would give us lithium fluoride as a product and bromine. And then finally, we have C2H6 reacting with O2. This will be combustion because I have O2 as a reactant. Now remember, what will happen is we'll form a couple of oxides here. One of the oxides will contain carbon, the other will contain hydrogen. And as I mentioned earlier, our products for this, anytime we are burning a hydrocarbon, meaning a compound based on carbon and hydrogen, we will always get carbon dioxide and water. Alright, last practice here. I've given you 3 reactions. Predict the products for each of the reactions. So pause the video, work through it, see how you did. Okay, now that you've had a chance to practice this, let's see how you performed. The first one, we have copper 2 nitrate reacting with sodium hydroxide. This is going to be a double displacement reaction. I know that because I have 2 compounds, so the cations are going to switch partners. So the copper takes the place of the sodium, sodium takes the place of the copper. This will give us copper 2 hydroxide and sodium nitrate. Again, notice that the charge in the copper ion remains the same. It's 2 plus on the reactant side, it is still 2 plus on the product side. For B, we would predict a single displacement because we have a free element reacting with a compound. So the free element will take the place of the cation in the compound. So in this case, the potassium will displace or replace the magnesium. So that's going to give us potassium sulfate and then magnesium as the free element. Finally, on C, this will be synthesis and combustion. It will be both because O2 is a reactant there and we're reacting with another element. Probably easiest just to think of this as synthesis. So the silver and the oxygen will combine to give us silver oxide, which is Ag2O. Alright, the predicting the products, there's a lot there. The next video is designed to clarify maybe some confusion you might have. There's a few more details that were not discussed in this video. That video will focus on the displacement reactions, the single displacement and the double displacement reactions, to help clarify some things and also to provide you with a little more detail as far as how those reactions occur and then why they occur, and in some cases why they will not occur.